In this work, we are investigating the effect of different welding techniques on the mechanical behavior of low carbon stainless steel. In fact, in Egypt, we have good technicians in Gtaw and Smaw techniques. Therefore, we performed this basic study in order to evaluate the effect of these two welding processing by Gtaw and Smaw. So this is a basic study about the mechanical behavior of low carbon steel, weld joint by Gtaw and Smaw techniques. Also, welding at different heat inputs was investigated. As you know, that low carbon steel is used in 70% of the structural materials, such as manufacturing of pipelines and boiler wall tubes and more structural. Therefore, the welding of low carbon steel has a significant importance for the industry. Therefore, we did this basic study. However, also we are planning to perform more investigation later about this study. The material, now here it is only one material, it's low carbon steel, grade S275, and it shows perlite and ferrite. And we have like 1.24 manganese. For the methodology, we investigated the process of Gtaw technique. At this technique, as you know that we use that external ferrule metal. So if we don't use that ferrule metal, then it will be autogeneous welding process. However, now it became non-autogeneous due to the external ferrule metal. And here in the shielded metal arc welding, we are using that coated electrode for the welding process. Therefore, here we use the shielding gas of argon in order to prevent oxidation of the weld zone. Here is the welding parameter. For Gtaw, we used 3 different heat inputs, 187, 200, and 250. And then for the Smaw technique, shielded metal arc welding, we use extremely high heat input, 280 and 317 joule per millimeter. And the same also after welding of the plates, we got some specimens for microstructure hardness and tensile testing. And also we used microstructure analysis via a software program which is called MHA for image processing of the microstructure. Regarding the results for the Gtaw welded joints, we found that in the fusion zone, with the heat input increase, there was some increase in the size of the grains. Furthermore, also this happened for the heat affected zone. Regarding the fusion zone, here this is a basic study. We did not use EBSD. Therefore, we're still not sure about the fusion zone, whether it contains martensite or enite. But we use that software program in order to analyze the weight fraction of this formed phase. And we found that this hard phase is decreasing with increasing the heat input. As we said in the previous study, that this is a similar. When we increase the heat input, then the size of the fusion pool is increased, and this affects the cooling rate. Therefore, When we increase this heat input, cooling rate is decreased. Therefore, if this one is a martensite, then the amount of martensite will be decreased with decreasing the cooling rate. And for the Smaw technique, we also got a similar structure. However, due to the higher heat input, we will find that the fusion zone displayed like elongated grains in the direction of welding because we used relatively high heat input. And also for the analysis of the structure, we found that this amount of that phase is decreasing, like we got only 0.6% of the martensite or benign phase. Also, we performed this profile hardness measurement, and as expected also, at the lower heat input, we will get higher hardness. However, we increase the heat input, then the hardness will be decreased. Also here for the Smaw, but in some points we found that the lower heat input was giving higher hardness in the heat affected zone, but in the fusion zone also we found that the higher the SM2 gave like about 300 HV. Regarding the mechanical properties of the welded joint, here we found that the joint efficiency for the lower heat input was only 92. Then when we increase the heat input, the joint efficiency was increased. It recorded 69%, and the fracture was located at the heat affected zone. The same also for the Smaw. Then when we increase the heat input, the joint efficiency was increased. Like in a conclusion of this study, that the heat input increase will improve the joint efficiency, but it has an negative effect on the hardness values. With the heat input increase, that the molten pool size increased, and grain coarsening at heat affected zone is promoted, leading to premature failure of the welded joint that has hardness was decreased with the heat input rise, and joint efficiency was improved with the heat input rise. That's all for this talk. Thank you.